So today we're going to switch language, and so we're going to go through the language Fortran, but in the modern way. So if you have seen Fortran before, you've probably seen Fortran 7.7 code with very fixed formatting. We will not teach Fortran 7.7 here. Fortran 7.7 is compatible, but it's still but I will kind of go through how it should be done from Fortran 90 and onwards. So some parts we're going to go through. Of course, back. We're going to go through history, how you write your write your code, the source form, program structure, compiling code, variables, operate, and the normal things. I will go through a larger example as well, how you structure your code, a little bit about the array feature that is built into Fortran, input and output. And we will see how far we come. There is a second lecture of this as well, so I will go through some starting points today. I will also show you how you compile code and run Fortran code. So a question that arises perhaps is, why modern Fortran? So why should you use a language that is from the 50s today? And I also said that advantages of a standardized language. And I think that one of the things that you see with Fortran is that Fortran has almost all the time been a standardized language, an international standard, which also have made it live a lot longer than many other languages. So I just standard language has been continuously developed. The latest version now is Fortran 2023, and it has been largely backwards compatible many years back. And if you can't get it to be compatible, or there are things that have been deprecated, you can always link to Fortran 77 code. You can compile it separately using Fortran 77 and then link it together. But basically you can use most, I would say 95-96% of all the code from Fortran 77 directly, compile it with a modern Fortran compiler. It's also optimized for high performance computing, so there's a lot of structures in Fortran that is for working with arrays and so on, which is built into the language. If you compare to, for example, C and C++, array is a native data type in Fortran. So then you say perhaps C has also a native array, but it's only a one-dimensional array. In Fortran, you can define 1, 2, 3, and multi-dimensional arrays, and it's built into the language. It knows how to deal with those. And also, most of the functions in Fortran are also can also be used on arrays by default. So if you give the sinus function an array, it will compute the sinus of all the elements in the array, just like you do with NumPy in Python. Many of the standard operators also work on arrays. Also, the modern part of Fortran has also introduced something called modules, very similar to what you have in Python. A bit more, you have to add some code to define modules, but they are there. And they're a very good tool to structure your code. Also, in the later versions of Fortran, you can write fully object-oriented code as well. And that is implemented using an extension to the derived data types, which I will go through today as well. And it's also a very nice language to create extensions for Python. So there is a tool, which I will go through in a coming lecture, called F2Py, which takes a Fortran code and compiles it to a Python extension. So you can use the high performance of Fortran and quickly integrate that into Python code. So a bit about history. So first version was introduced in 1954. It was, I think it was called Fortran 0, Fortran 1. We had a standard Fortran 66. We had Fortran 77. And those were released approximately at this time as well. And a major change was done in Fortran 90. So Fortran 90 did a major revision of the language. So introduced fixed form source code, which I come to later. So you can write the code just like you do with C++. Long variable names, dynamic memory allocation, a lot of that stuff that was common in other modern languages at the time. So I would say modern Fortran starts with Fortran 90 and above. There was a short interim language called F where you skipped the backwards compatibility and just allowed modern features. Didn't fare so well, so we haven't seen a lot of that language after that. There was then you have continuous standards here, Fortran 95, which introduced some high-performance computing constructs, Fortran 2003, 2008, 2018, 2023. So it's continuously developed as an international standard. The standardization group around Fortran is not as big as C++, but it's still a large group, and they continuously add features to the language. I want to compare some code here. So this is a Pascal program with a function and a loop. And I also have a C, corresponding C program here that does the same thing. Just to have those in mind when I go through the different Fortran language developments here. So if we start with Fortran 0, Fortran stands for formula translation. So the first idea with Fortran was to create a language that could translate expressions in a standardized way. Because before Fortran, every computational code had to be implemented in machine code or assembler, which was a problem because you have a lot of machines. Every machine that came out was different. So with Fortran, you got a tool that could take your expressions and translate them into machine code in a platform-independent way. You have here the line numbers here. You can also see that it's a very fixed form here. So you have certain column means certain things. So here you have the row numbers. And you actually, for do loops, for example, you need to specify the rows where they... So this is the loop starts at 3, and it loops around 8, and if the loop is finished, it goes to 11. So the line numbers were actually, you had to specify them. You can print out things as well. You have go to statement, which is not so popular today, or you should avoid them. So instead of doing end do, you do go to 2 here to go back again. So this is the first iteration. Fortran 1 introduced some more stuff here. You have you can define functions. You can have comments. You can define formatting of output. So how you want to print on screen or a printer in that case. You got the do loop that was a bit more improved. You only had to specify where it should continue here. So you have a continue statement as well, that instead of having a go to for the loop. And then the continue statement there. Fortran 77, you got more stuff. You have an if, else, and if statement here. That was new. You can define a program structure, so the name your identify your program, the program start. You can define separate functions that could be separately compiled in different files or after your existing code with input parameters as well. And if you look at modern Fortran, looks something like this instead. So this is more like the Pascal version that we saw in the beginning. You start with a program here. This is the program is where the program starts. You declare your variables here. You assign your variables just like in Python. You use write here to write to the screen. You call a subroutine here. And you can have a subroutine here in your contain section or program. And then your end program here. That is the end of your program. So that is the kind of simplest form of, I don't know the simplest way, but this is the typical structure here of a single source code program in Fortran. So no line numbers and stuff like that. So there are different flavors of Fortran at source. And freeform was introduced with Fortran 90, and fixed form is the form which has been inherited from actually punch cards. That's far away. And the fixed form you had, code was in position 7 to 72 columns. You have line numbers in columns 2 to 5. You had comments were put in position 1. And you can also have a character on position 6 to get an extra continuation of the line. And you can only have one statement per row. So with freeform, you have max 132 characters per line. You can have comments anywhere on the line using an exclamation mark. If you want to continue a line, you can put an and character at the end. And you can have multiple statements on a single line using semicolon. So this is according to standard. I think most compilers today can have longer line numbers as well, but be aware the standard says 132 characters. So it could be that you get to a compiler somewhere that doesn't like 132 characters. So just because it compiles doesn't mean it's Fortran. That's what I want to say. So here is some example of this. You can see here that you can have a comment anywhere on the line. You can have and here to continue to a new line. Same thing here. So this is a single line expression. Here you have multiple statements grouped with a semicolon. It doesn't mean that they execute at the same time. It's just that you can put multiple statements in a single line. So the basic structure of a Fortran code. So this is the syntax of a program, a main program in Fortran. And it should be let's see here, it should be like that. So you see, the brackets here are optional things. The only thing that you have to have in a Fortran program is end. So the smallest Fortran code you can write is end. The other things it's good to have, I would say. So it makes your program more readable. So the structure is, if you come from C++ or C, you can intermix variable declarations wherever you are in your code. In Fortran, you always have to have the variable declarations in the beginning of your code, in a beginning of a subroutine, beginning of a program, and then you have followed by executable statements. Then you have a contain section here. You will see that later in modules, where you, after the contain section, you can add subroutines in your main program.
Quick question.
Yeah.
In the first Fortran 0 and 1
Yeah.
show, you ended those small programs with a stop.
Yeah.
And this in modern you end with ends.
You can have stop as well. So
You can use both,
Yeah.
and stop is legacy.
a stop has more functionality.
Okay.
So a stop actually you can give it an error code and stuff like that. So it has been expanded. So
Right. But not end. That's just simple end the program.
and the program is
Yeah. Thanks.
I'm not sure if you can have it. Yeah, you can have it in subroutine as well. Subroutine also end. You can usually have end subroutine, but I think you can have only end as well.
Stop will kill the program.
Yeah.
Or just
it's a delimiter. In the main program here, it's the end of the program.
Yep.
But in subroutine, the end is not end of the program. It's just end of the subroutine. It's if you don't have a return in subroutine, it will actually return to the calling program. So compiling and running code. So Fortran is not the same as Python. Python executes line by line. There is no discrete compilation step. You just execute your code using a Python interpreter. In Fortran, you have to convert your source code to a binary code in some way. So you have to go from source to executable using some techniques. So first, what is a program or executable? So a program is executable code in machine code. So basically that is just numbers that contain the machine instructions for your processor. So basically it's very hard to read. Together with that, there are links in your executable that interacts, so that kind of connects your executable with runtime libraries of Fortran, but also for system libraries connected to your operating system. And then you have also the external libraries. If you have a math library or something, you link that together. So this kind of produces a program executable. We combine these together. Executable code, that is your code. You have linked to system libraries that are printing out to the screen, talking to the operating system, opening files, and then you have other libraries that you depend upon and use. So you can build an executable in multiple ways. You can hand code machine code. If you can just enter numbers and try to execute that, that's really hard. You can write in assembler code, which is a bit higher level, where the machine instructions are given as mnemonic symbols that you can write. So it's more like a programming language, but it's specific to the machine you're coding for. So you have, for the Intel architecture, you have the compilers that have an assembler that is with the Intel specific instructions. So it's less hard. But it's easier if you're using Fortran, because Fortran and C and C++, they go on a higher abstraction level and compile directly down to machine code. Python, easiest. It doesn't, the machine code is kind of line by line. It translates one line and translate that into machine code at some point, but it does that every step in your code. Actually, Python actually translates your code into intermediate form, but it still executes line by line. So to create an executable for a high-level language, you have to write a source code file. You have to compile the source code into object files, which are unlinked machine code files. So that basically machine code that has hooks to calls and stuff like that. And then finally, to get the final executable file, you have to use a linker to connect these object files together, and also to link with system libraries and to create an executable. And this process is very similar on all platforms. They use different compilers, different linkers and so on, but it's the same process. You have your source code, you have to compile the source code to machine code in object files, and then link them together to an executable. This is the high-level view of this. You have your source code files here on the left side. You have a compiler here that will generate now this is Linux or Mac. You create an object code file, that is a machine code. Each of the source code file will have a single object file. You have libraries, could be precompiled math libraries that you want to use. They come here as well. Then you have a linker step here that looks on all the object files, resolves the calls, and creates an executable. And I will show you how that can look on a, let's see here where I get my, so now I'm in a directory here. I have a single file here. So my first.f90, if we look at that one, I'm running this on a Windows machine, but I'm using a GNU compiler here, so it's the same compiler command as for on a Linux machine. I type gfortran, which is the compiler name, give it the source code name, my first. I could just press enter here because the gfortran compiler does the compiling and linking in a single step, and by default it will generate executable as well, but perhaps with a strange name. So it's on Windows it's called a.exe. and I can execute that one. But usually instead you do G Fortran my first, and then you press -O for output, and give it your own name here, my first, like that. And if I look here, I have a myfirst.exe here. It prints out hello Fortran. So that is on a Windows machine. Didn't I have? Yeah, I had it. So sorry. I have it here. So I have actually logged into the Cosmos machine here as well. Let's see if we can just do. So I create a source code file here, program. I start, so my first, and then I do print star hello Fortran, which you should do. Always have to do some my, and then program my first. So all of the things, the program my first is optional, and program my first at the end is also optional. Then I log out here. So the first thing you have to do to compile this is you have to select a compiler. So what you do is you use the module command. You can say module avail here. You can see here we have a lot of software installed. And what we want to use here is you can see here there are tool chains here that contain all the compilers that we need, and they are compiled in different. So they release 2 tool chains every year, and so they update the compilers every half a year. And what we should do is we should load a FOSS 224A tool chain. That means that we free and open source software compile. That is all the GNU compilers. So we do ML FOSS 2024A. And now I can ask which compiler do I actually have. So the G Fortran, you can see here I have GCC core 13.3. So that is the 13.3 version of the GNU compilers. I can also ask G Fortran here. It's 13.3. So now I have a Fortran compiler, and I have my F90 file here. So I do the same thing, G Fortran my first -O my first. And on a Linux machine, or you can't just execute it like in Windows. You need to do /.myfirst like this, and then you have Fortran. So it's a bit different from Python. Here you need to kind of translate your code and then link it and get an executable. And the nice thing with the Fortran compiler, it actually does a lot of that stuff for you automatically. If you have multiple source code files, you can just add them here after my first here, and it will compile them together and create an executable. So you can also, there are also Intel compilers, which can be loaded by the corresponding commands. Yeah.
Do you think I will run into trouble in this course if I use the homebrew?
No.
Compile?
Just that you have a GNU compiler.
Right.
Yeah.
Yeah.
They have a bit in the naming scheme is a bit, so you need to kind of figure out which. It's not called G Fortran. It's a G Fortran dash version something dash.
This one actually now it has an alias.
Okay, good. Yeah.
I just happen to have it.
Yeah, it works perfectly. Yes, so the Intel compilers can be used on Cosmos as well using the Intel toolchains. There is also, if you are running on the desktop, you can search for the different versions that are available here. Yeah. We have a lot of different compiler versions installed. And you can also, you can compile a Fortran code. If you just want to do the compilation to an object file, you can use the C command. That will compile to an object file. And that is useful if you want to combine it with other, for example, C code and stuff like that. You can link it together separately. And the .o file here is the machine code, unlinked machine code. And you can do multiple source code files at the same time, and that will produce source 1 and source 2. And then, of course, you need to link them together. And then you can use gfortran as well, because it's also a linker. So if you do gfortran my source O, will generate an executable from that object file. You can also give it just like a name here, as we did before. So you can do a two-step process, but you don't have to with Fortran. You can just give your source code file and compile. It will do both of those steps at the same time. Yeah, I already showed you that. So, but here you can see you can do my source, source A1, source 2, output my exit. It will compile the source code files and create an executable.
How careful should I be with my file extension here? Any strong conventions?
I usually do Fortran 90 for modern Fortran and above. You can do F03 and stuff like that as well. But usually it works best if I do F90. It works for most things. But you shouldn't use .f because that is fixed form. And so there are some distinctions there. But F90 is free form, modern Fortran.
Will the compiler complain about that, or is it mainly IDEs?
Some compilers will look at the extension and enable certain things in the compiler.
Right.
But usually I have never seen a compiler really do that. Most of I've compiled all my examples are F90, which also contain all the 2018 features. So there is no distinction there. So now we're going into the language here. So variables. So it's similar to what you do in Python. So variables are named storage locations in memory that can be modified during the program execution. And the compiler will allocate memory for the variables according to the data type of the variable. And I said it with reservation here. So you can also allocate memory yourself using dynamic memory allocation. But the variable I'm talking about here is the one that you declare. The compiler will reserve memory for you automatically. Naming a variable. So in modern Fortran, you can have 1 to 33 alphanumeric characters in your variable names. And you can have both uppercase and lowercase. And also Fortran is case insensitive. So regardless of uppercase and small, if you have the same characters, they will mean the same. So A and lowercase lay are references to the same variable. Also, the first character can't be a number. So valid variable names are shown on the left here. So you have A here, that's a alphanumeric character. You have underscore, the second character works well, X and a number, and so on. This is not invalid because you have a 1 here, not valid because you have a 1 starting in the first position. Space is also not allowed. Also, you can't use only a non-alphanumeric character. You need to kind of have a character and a non-alphanumeric character in your variables. The kind of basic character types that are built in are integers, real, complex, logical, character, and derived types. So there are the basic building blocks of your variables. And many of these exist in multiple forms, so you can have a precision as well added to this. So you can define them in different precision as well. But you can see here that it's a language for computing. We have complex numbers built into the language. You declare variables by specifying the type, and then you have a attribute list here that defines some attributes of your variable, and then you have the entity list. There is where you specify your variable. So you can, in a single line, you can declare multiple integers, for example, by specifying commas after in the entity list. You also don't have to have colon, but this is usually what you do in modern Fortran, that you have integer, colon, and the variable name. Here are some examples. So you have an integer, colon, A, so that is a scalar integer variable, real, colon, b, scalar floating point, and so on. Logical is a Boolean variable. You can quickly allocate arrays by specifying a parenthesis after the variable name. That will create a one-dimensional array consisting of 10 elements. Two-dimensional array, 20 by 20, same thing. There is a second form of that. That is, you can do integer, and then you can give an attribute called dimension 10, and then you can declare a C will then be a 10-element array. And this here you can use if you have multiple variables that will have the same dimensions. You can just list them, and they will use this attribute, all of them. So this will be applied to all of the variables. Character, a single character variable. You can have an array of characters, which is not the same thing as a string. So if you define a string, you define it character, and then you give a special declaration syntax here, len 80 here. That will be an 80 character string, not an array. And you can have an array of strings here of the length of 80. So you can see this will be the kind of the string type that is a string of length 80, and then you have the variable or arrays of that. Constants are another variable-like type. Those are named values that can't be changed after they have been defined. And the compiler will enforce immutability of those constants. And in Fortran, you declare those constants just like any other variables, just like you add an attribute called parameter in the declaration. I didn't have a good example of that. Okay. Another thing is that you can specify the precision of your data type as an argument to the data type declaration. And the problem with Fortran here is that Fortran has a long history, and the precision specifier are compiler and system architecture dependent. Yes.
Huh?
Yeah. So you can't be sure that if you specify a real 8, that means the same thing on all systems. Now, mostly on Intel, in the Intel world, on the new ARM world, it means approximately the same thing. But you can't be guaranteed. So if you run on an exotic high-performance computer that doesn't have an Intel processor, you need to kind of make sure that you have this common precision on all platforms. And there are special directives you can use. So, for example, selected real kind can be used to specify the precision of real variables, and select int kind for integers. And those are not functions in the normal sense. They are compiler. At compile time, it's queried, so that you can assign a constant for the precision. So here you have you can do like this, real 8, real 4, and usually in Intel world that means that you have the top one is double precision, and real 4 is single precision. But it's not guaranteed by the standard. So what you do then is that what most people do in Fortran, they declare as constant here. So you can say integer parameter. That means that RK will be a constant in your code. And then you use the selected real kind definition here I want to have a 15 decimal places in precision, and the exponent should go from -300 to 300. And then you give that as a parameter here instead. So real kind equals to KF, or just real KF will... This is wrong here, sorry. It should be RK like this. And then X and Y will get the right precision identifier.
And this is stable across platforms.
So
this is a good approach across platforms.
Yes. And there are also, I will show you that there are also a way that you can actually, I want to see data types. So that there is a special model in Fortran that you can get the identifiers for the C data types.
But if I don't specify precision, there's no issues.
No, there is no issues.
The specifiers explicitly here.
Sorry?
It's the specifiers that are the problem.
Yes.
No.
Or the standard says that they are system dependent.
Yeah.
So it's up to the compiler vendor to define them. Today it's Joachim at Lunac will probably yell at me when I come back here. But usually 8 and 4 are the common ones that's double on single on most input compilers.
But if I don't give any precision, will that be
if
the same on all platforms, or will I see variations?
Yeah, so for example, you can give a real without a specific precision specifier.
Right.
Then it's system dependent which data type you will get. But in the Fortran standard, you will get the smallest one.
So, but it will vary across platforms potentially.
Yeah, it will be a big, but it will be. Yeah, it will vary because it could be that the compiler uses a different form for the real. But in Fortran also you have to be careful because in many other languages they take if you don't specify anything you get double. In Python you always get the double even if it says float, that's double. But in Fortran because of the long history they decided to because to save space, real is the lowest form, so that's a single precision. So here you can see how it's defined. So significant decimals, and then you have the range here from 10 minus 300 to 300. And another thing that is important is that you need to specify the precision on your scalar values as well. So for example, if you want to have 6.2 be stored with full precision, like you selected here, you need to add the suffix rk. And you probably see that a lot in Fortran code. And what you can see here, the effects of this is I have declared two AP selected real kind here. I declare these two AP pi1 and pi2. And I declared this one here with the same number of decimals here, but without the suffix. And pi2 with the suffix. And I print them out, and you can see they're different. This is a common Fortran mistake. You lose a lot of precision with this. And so you have to be really careful. If you have scalars in your source code, scalar constants, make sure that you have suffixes on them.
Because when the compiler reads the number.
Yeah, and it tries to store it as less space as possible. Yeah. So that's why you get this will be a real store. So real 4. This will store in a real 4 bytes. Approximately, because it's not system dependent, but the least amount of space it can do. And here you say store it with full precision. Another thing that we have not gone into too much here, if you don't say anything, by default variables does not have to be declared in Fortran. That sounds strange, but there is something called a general type rule. And that was defined somewhere in the 50s or 60s. And variables starting with I to n are integers, and other variables are real by default. And I can't stress that you need to declare your variables. And so this will lead to bugs if you don't do anything about it. And there is a directive in Fortran that you should apply everywhere, implicit none. That will force the compiler to check every variable declared that it's declared. Otherwise, you get if you kind of mix and match that you declare some variables, other variables are using the implicit type rule, some are fixed. It's not good. So yeah, this is how you assign variables. It's very like Python and C, but you see here that we have the precision specifiers. If you have Boolean variables, you assign them a special character string called .false and .true. Strings can be assigned using either single quotes or double quotes. There is no raw strings. This is what you get, not more and no less. I can also say that the newer standards in Fortran actually allow Unicode as well. So you can have Unicode in your Fortran code. Yeah. So you can probably do nice smileys and stuff like that in your outputs.
Just to follow up on the precision thing again there.
Sorry?
So if I have these numerical things lying around in my code,
Yeah.
I can take a chance and say, well, this will be stored in sort of minimal space, so it's fine.
Yeah.
Or
You should
be a good boy and always say that this is the precision I want for all concepts.
Yeah. There are some compiler switches, I would say, that can do that on the command line, the compiler command, or command line switch that will store your variables in full precision. But then you leave your source code to somebody else that doesn't do it. So that's, and also you have the flexibility because there are constants. You can have a single module in your code where you control the precision. So in that sense, it makes your program a bit more flexible as well.
The numbers in code should be specified to some percent.
Yeah.
And how you define real 8 or real 4? Explicitly, should you?
If you do real 8, you have to be it's better than just real, because it's explicit. But there is nowhere in the standard that says real 8 is 8 bytes, even if it's what it does by default. So you should define a constant and replace all your 8s with a constant in your code. But if you have real 8, you're pretty safe. But my recommendation is still that you define selected real kind and use that constant in your variable declarations. There is another way of doing it using the ISO C module in Fortran, which defines all the C data types. Then you can use those in Fortran as well. You don't have to define them yourself. Another thing is that there are two states of variables. In Python, a variable is always kind of has a value. If you create a floating point, it will be 0 and so on. It will be initialized by default, except for NumPy arrays. But in Fortran, they have two states. You have undefined variables and defined variables. And an undefined variable is when you have a declared variable, but you haven't assigned anything to it. It's considered undefined. And it's defined when you assign it. And if you have an array, it's considered to be defined when all elements have been assigned values. If you just have a single element that is not assigned, it's undefined. And arrays are not initialized by default in Fortran. So if you allocate an array 20 by 20, it's not 0, just so you know. So you need to zero them out before you use them, or you read them in and fill them with data.
And the correct lingo there is you write down that this is array 20 by 20 or whatever, but it's not filled, so it is undefined.
Yeah.
Until every value.
Yes. It's just not something that it could be that you get some compilers have warning for this variable has uninitialized and so on, but it's because it's undefined. So the compiler will compile your code, but it will not. You have to give I think this is warning as errors to get it to complain about it. There is another data type that is called the derived data type. Sometimes it's easier to define your problems when you can define your own data types. So we already went into that bit with Python with classes. Classes are derived data types similar to in Fortran. So you can define a group of variable types that together becomes another data type. And you define them using the type keyword, and you give it a name, and then you give it a variable. Let's see here we can have here. So here you have, for example, a particle is a typical derived data type. So type particle here, that is a new data type we have invented. And it consists of 4 floating point values. And then you give n type here particle. Now we have a new data type. And because that's not part of the language itself, we need to use a certain declaration here. So type particle instead of using particle directly. And P is now of the type particle. And here you see another strange thing with the Fortran, that you don't have the dot specifier to access the elements in your derived data. You have the percent operator, which is, I don't like it, but that's the way it is. So if I want to assign x here in my particle type, I do p%x equals to 0. So it's very similar to the Python attributes that you had. But in Python it would be p.x. And here is p%x. And then you can print them out like this normally.
And the position here is just not defined from C, or is dp something into
So the position?
the precision?
Yeah, it comes from, it's built into MF utils here.
Oh,
It has constants for that. So if you, in the GitHub repo for the modern Fortran book, there is a directory with two modules, one called MF utils and one is called MF. These you can use yourself, and they have some predefined constants that I use in my lectures and stuff like that. Yeah, and you can also, you don't have to have just real, you can have real, integer, logical, character, of course, in this. And you can store them in arrays as well. And here we come back to these data types again. There is some new module here in the, I think it came in the 2008 standard, called ISO-C binding. And that defines all the variable types in C in Fortran. So if you use that module, you will get C float, C double, C int, C long. And then you can declare real C float x. And then you know that this will correspond to the same data type as the C compiler, the GNU C compiler.
And that's platform secure.
Yes, at least between the same project. There's another module as well that actually gives you the ability to use bytes in the declaration, so real 8 and stuff like real 64. So here you can see here, use ISO-C binding, and then you have these variables available for you. Perhaps a 10 minutes break, and then we continue. Operators and expressions. So this is kind of the most important part for your numerical language. Let's see here. You have the common ones. You have power of, 2 multiplication signs, 2 stars, multiplication, division, addition, and subtraction. And this is also the order of operation. So it's evaluated first power of, then multiplication, and so on. Yeah. Order of parentheses, operations with power of, application of division. Very similar to other languages. There are no big difference there. Relational operators here, of course, we have legacy from the 50s. And that means that because you had a character set that was limited, you needed to express less than and greater than with characters. So you have less than here, which is the modern one, and .lt. Both of them work. So you have less than equal, greater than equal, equals to with the double equal signs, and then not equal with a slash equal. So it's almost like the Python version, but without an exclamation mark. Slash equals is not equal to. You have logical operators and, or, not, and those requires you to have dot and dot or dot or dot. There is no, you have to do that.
There's no easy
No.
F90 version.
No, not. I mean, the problem is that they have so much legacy, they can't change it. Also, results of division are truncated towards 0. Yeah, and also that this here will be 0. So it doesn't do like in Python. goes to the higher part. It actually, you have to think about things like this. Mixed mode expression. So if you have a expression consisting of real and integers, the integer will be converted to real in the before the expression is calculated. That is a good thing. And also, most of the expressions can also apply for arrays. And when you are working with arrays and use the normal operators, you need to make sure that the arrays have the same sizes. Otherwise, it doesn't work. So it's not as flexible as the NumPy arrays. You need to kind of think about the sizes before you do the operations. So if you have an expression with an array and a scalar, that scalar will be added to all of the elements in the array. And order operation is not specified as standard. That means also that compiler optimizations can affect the performance of these array expressions. So here's some examples here of. So I have two-dimensional arrays, one one-dimensional array V, and if you do A divided by B, that means that the result of that expression will be Aij divided by Bij. So element-wise division on all elements. If you do V plus 1 dot here, it will add 1 to all of the elements in B. And here you have 5 divided by V, so that is 5. So all elements in, it will be 5 divided by the elements in B, and then A plus that array that is result will be added. We take one slice of A here and add that together. Also, you can do A equals B, and that is true if all Aij, Bij are equal. Otherwise, it's false. So arrays is important concept in technical application, and it's also very efficient data type in Fortran. And there are two ways of allocating. You can do static arrays, that is when you explicitly define them at compile time, and you can also dynamically allocate. I come to that later on here. They also support advanced indexing and slicing that you normally find in MATLAB and Python. You can do that in Fortran as well. By default, all arrays in Fortran has a starting index of 1. But you can actually redefine it. So what you can do here is you can set -3 to 3. That will be an array that has an indexing of -3, -2, -1. So you can actually redefine it and have a zero-based index as well. You can assign arrays by specifying parentheses. So Fortran does not have square brackets for indexing. It has normal parentheses. That's a bit different. And then you give the row and column and then the value. But you can also do like this, k equals to 5. That will assign all values in the array the value 5. You can also assign them using in your source code. Then you use parenthesis slash, and then you just give the numbers like this, and then end with a slash parenthesis. So this is a nice way if you want to assign arrays that are predefined in code, that you have one row per line, and you give them using this notation here.
You have the shorthand version as well, that you say k plus equal 5, for example. If I want to add 5 to that.
There is no plus equals operator. But you can do k equals to k plus 5. Yeah.
But I need to write k.
Yeah. You can also assign slices. So I have a 4x4 here, and I have 2 one-dimensional arrays, 4 and 4. And what I can do then is B, which is a 4 one-dimensional 4 elements. I can extract column 2, no, so row 2 and all columns to B. I can do the same thing. I can do all rows column 1 with column 1. Very similar to MATLAB, and you only have to think about that you have the indexing right. There is no checking of indexes, so you can do a lot of it can go outside, but usually if you stay in the indexes here, it should work fine.
So these two slices from A there, so it's one-dimensional arrays. There's nothing mysterious going on in terms of directionality or whatever.
No, performance. That can be some.
Or 4 by 1, for example.
Yeah, there could be some. I think it can be. The efficiency could be different depending on which direction you slice.
Okay.
Because if you slice in a certain direction, you have to have a stride, and that could be you can miss the caches in the memory if you do like that. So, but other than that, there is no magic here.
I will get 2 different one-dimensional arrays.
Yeah.
Right.
And same thing here. You combine this here to. If you want to assign a single line in a single row in a array, you can do K5 : then have this notation here. So you can have 1, 2, 3, 4 in separate rows and assign them like this. It looks kind of nice in code. Yeah. Yeah, I think we came into this in Python as well. How you store in memory. So arrays are stored as one-dimensional arrays in continuous memory. And in two-dimensional arrays are stored column-wise in memory. So compared to C, which is stored row-wise. So if we have a array storage like this is stored linearly in memory like this. But you can also see it like a real A by 2. Then it's stored, you have first a column here, and then a second column here. And if you have 2 by 8, it's stored 1, 2, 3, 4, 5, 6, 7, 8, and so on in memory. And this is the difference between C and Fortran. We have different conventions with regards to storing arrays. And if you are in NumPy, I will come to that when we do mixed language, you can create arrays with order equals to F. Then they will have the Fortran ordering, which you can pass the arrays over to Fortran directly. Yeah, you can also have arrays as derived data types. And this here, let's repeat it again. Conditional statements. Yeah, so this is also important how you kind of define your flow of your code. And we start with if statements. The simplest form is just if parentheses. You always have parentheses for the expression, and then a single statement that is executed if the expression is true. Then you can have a if an expression, then, and then a code block, and then end if. And then you can group them together in multiple ways here. So you can have if expression, then, else if, it's another expression, else, block, end if.
But only signal line if I don't use the then keyword.
Yes, single line statement.
You can.
Yeah. So if you want to have multiple lines, you need to go with them.
Yeah.
But if you have a single thing, you can just do one line. Right. So here's an example here. You have if x greater than 1000, then do this. If less than here. And also if you have a Boolean here, logical, you can do if flag here. But you always have to have the parentheses in the expression. So you can see that if is kind of a function in the set. Then if you have a lot of statements you want to test, you can use the select statement instead. And that is similar to the switch statement in C. So select case expression, case something from that expression, then you do that. And then you can just list them together. And then if none of the case selectors match, you will have a case default that can be executed as well. It's kind of a fall-through statement.
That provides an interesting case because in C, different compilers complain a bit if you sort of make these cases mix with each other.
Yeah.
So in older versions, there's sort of a problem if you use case this and then don't break it off before the next case. It's intertwined and you assign variables.
I don't know
it's a bit of
anything
an
about
edge
that.
case, but I mean, you have one case. Do you explicitly break it off, or
No. So it looks.
Will just continue.
It will not.
Or
it will execute this line only.
okay.
So it will be kind of a code block, code block, code block.
Right. That is kind of very different from C.
Yeah. So if we run this here, I can. When you see some green buttons in the slides, you can open them in Compiler Explorer. And if you haven't seen it, this is the super cool tool. It's a compiler online. So you can put your code here and you can execute the code. You can also look at, it's a bit nerdy here, I think. Yeah. You can see the machine code or the assembly code for the compile, what is compiled. And this also is very clear when you do activate the optimization switches in Fortran. You can see how the code changes, how much code is executed. So you can see here, for example, the blue here is here, and then you can see that it's different code is coded color differently depending where you are in the code. Yeah, you can see here. So now it's unoptimized code, so that's why. But what we're going to do here, let's see if I can get the. Open it again. I just used it to kind of show the output here. So it's very easy to, you can see here that this is the code output from the code. And you can see here that when the value is 3, it's only executing this one here. If I change this one here, you can see it automatically compiles and it says number 1. So here you can try out yourself the different, what happens in your code. And in the book there is a lot of try this button here. You can try your code yourself and test.
I guess you can pick.
What's that?
I guess you can pick compilers here.
Yeah, that's also the cool thing.
Yeah.
So here you have you can select the language. You should be able to select. Here you have the Fortran compilers.
Nice.
So you can try every compiler there is basically. MIPS Fortran, you have Power Fortran, you have Microsoft Fortran, all the compilers available. And there are, of course, other languages here as well. So it's a really cool tool to look at what actually happens when you compile code. And if you add, I think you can add, can't remember now exactly how I... Compiler options here, yes. You can do, for example, O3. Then you can see the code changes here. It's shorter. So it optimizes away a lot of things. And here, these are the assembler instructions. So it's not machine code, it's assembler. So this is where the kind of intermediate form before going to machine code. But if you change here, for example, to take a ARM compiler, you can see you get different commands here. Yeah, so that was just and I think if there is a green button, you can click that and you get to the example on Compiler Explorer. Repetitive statements.
Can I ask a question?
Yeah.
Does select work only with values or with
Sorry?
conditions? Does it work only with values or with conditions?
This one here. You mean the expressions here?
Yeah.
There are, I think you can have a...
In C++, it only works, switch works only with values.
Yeah, I think you only can use ranges here in the colon. So here you have from greater than 1 and but between 2 and 9. So you can't you want to have expressions there Or
Yeah, and then in select case, you can put, for instance, string variable,
Mhm.
and then check if it's equal to some other variable.
I'm not certain about that. I usually use it when you have kind of very distinct values that you want to check for.
Mm-hmm.
Can you technically use this as an if statement if you have a logic rather than numerical value?
Let's see.
Yeah.
I mean, it would be stupid because we have the if statement.
I can see what happens if we do another statement here. No, it doesn't like that. But then you are back to having if statements again. And I'm not sure you can. This is the comparison value. And
Comparison like equal or not equal. Only this kind. Or inside of the range.
He seems to not like it. Let's see if I can just.
So for integer values, it's easy to write those inclusive or non-inclusive. But can we evaluate total point values as well?
I think so. Let's see here.
And then inclusive or non-inclusive intervals becomes.
Can it be real?
Argument of select cannot be real.
So it
But
needs.
is that because how we structure the cases, or is
Yeah, I think so. So it needs to be an integer. So you can only test for integer values then. You can probably put variables in here if you have a integer parameter b equals to 4. Oh, it's okay. So you can have variables in here, but they have to be integer.
and overlapping cases? If multiple of them would be fulfilled?
Good question.
Are we executing only one or all?
If we do one more here, so
Let's say that goes from 8 to 10, for example, and you have a value.
If there is a break.
overlaps. Doesn't like that either.
Okay, so you only execute one block.
Yeah.
And they must not overlap. That's
Exactly.
interesting.
Yeah. So it's limited. Repetitive.
That comes from the tradition of using integers as flags for a lot of things.
Yeah.
In old ways of coding.
Exactly. Repetitive statement, you have the do statement. You start end value and you loop over. You can also have a third parameter that is a step. So it's very much like the range statement in Python. You can also control the flow of the loop, which I don't recommend if you can avoid it. It can be a bit spaghetti. But you have exit, that exits the do statements and continue after the loop. And you have cycle that continues to the next iteration. So that's the way you can control the loop.
Which would be break and continue.
Yeah.
So there is no more continue.
Sorry? No.
There is no continue command.
Well, it's
As it
cycle.
was in old Fortran code.
No, that's the old way of doing do loops. So have do continue. You don't have that anymore. So you have do and do.
So there is, I mean, you can't use continuous step cycle. Is it the same? What's the difference?
Let's try it.
The cycle seems weird command.
Well,
Continue.
back to the beginning.
But it didn't do the same thing.
Right?
So if I have cycle here, it stops at, so if less than 10, then cycle. So it doesn't print out anything before 10. So cycle goes back here, it doesn't print. If I put continue here, kind of a no operation, then it continues here, if statement, and goes from 1 to 10.
But it's still marked as a keyword.
Yeah.
It does something.
It's backward compatible. I think I'm not sure what actually continue keyword did in all4 because you always had to have a line number anyway. So I think it was kind of just a way of putting something on a row, and that is the end of the do loop.
All right. Well explored.
Then we have another form that is the do while. So you have do while and then an expression, and then continue execute until the expression is false. So this is, if it's true, it continues, if it's false, it go out. So here is a typical one here that you have iterate if do while x less than. So if this is true, it continues iterating here. If it's not done, it exits and continues after undo. So it's typically if you want to iterate over something. Then we have a lot of built-in functions. Not as many as we have in Python, but several of them, and they can be used both for arrays and floating point and so on. So we have the common mathematical functions. We have conversion functions, and we have vector and matrix functions. So we don't have a lot of matrix and vector functions. If you have a dot product, we have a matrix multiplication, because the normal multiplication operator is element-wise multiplication. So if you want to do a matrix multiplication, you have to use matmul. And also transpose is also a special function, and dot products as well. So those are the kind of major vector and matrix functions. Yeah, as I said before, you can use all the functions just like you have. So any functions in Fortran that is math related can take an array as an input, and then it will compute this function on all elements. So I'm going to do a bit larger example here now. It's not too complicated. So it's you see, I come back to mechanics again. So I want to create a stiffness matrix, and the formula is given above. You have the stiffness matrix KE equals to G transpose times G K element matrix multiplied by the G matrix. And it's basically doing some transforms here, going from local coordinate system to global coordinate system. So you have this expression here, and you have, this is the local element matrix. We have to calculate some length here, some directional cosines, and we want to implement this as a function that we can call. So here we have, I start with implicit one, none. I define precision constant. I declare all my floating points here real RK. And then I declare the sizes of all the variables here. And I make sure that I have RK as a suffix here on all of them, so that they get the right precision. I calculate the directional cosines. I calculate the local stiffness matrix here. I use two rows here you can see the structure of the array. And the KEL equals to KEL times this one here. So I do that as a second step here, and that will multiply all elements in this array with EA divided by L. Define the G array here, just using this notation so you can see the structure. And then I do the matrix multiplication. And I kind of start from within going out. So I have transpose G times K element. That will return one matrix, and then do matmul by KL here. No, sorry, I do transpose times then, and then I have multiplied by G at the outside. So it's not like nice NumPy expression, but you still have the possibility to do those things in code. So you don't have to do all the looping yourself. And then I print it out. I come back to formatting here, but just print out the matrix here. And you can see it looks like this when I'm done. So, building blocks of a program in Fortran. So we have a program name, I've seen it before, and you can only have one main program in Fortran. So if you have multiple source code files, only one of them can have program and program. To divide your program further, you can have multiple source code files containing modules or single codes that you link in. Just kind of, we come back to the stop statement again, that we talked about earlier. The stop statement stops the program execution. And you can use that in all your modules. And it will stop everything. So if you embed a stop statement in your subroutine library, you need to document that in your code, in your documentation for your code, because it will stop the entire program regardless. So well-behaved subroutine should perhaps return control back to the program and return some error code instead of having stop statements inside it. But you can also have stop codes that gives you a number or a string so that you can, okay, this program had a catastrophic failure. It was due to X. So that you can use the stop things as well. Yeah, then we can divide up our code in subroutines and functions. And a subroutine function is a named block of code that performs a certain task. And you can call these from different parts of your program. You can also have multiple arguments. We have done this in Python already, so it's very similar. Arguments in Fortran can be used to provide both input and output to subroutine functions. So there are differences here. In Python, basically you had input variables that could only be accessed inside. They were not going out for this interface unless it was a NumPy array. In Fortran, arguments passed to a subroutine. If you modify them in your subroutine, they will modify the variables that you call the subroutine with. So everything in Fortran is passed by reference by default. So you have to be a bit careful of that. So you can have I had a case when I was I used a library, and I passed my Fortran array over to the library, expecting that of course it doesn't modify my array. But that subroutine actually used my array as a working array as well for solving the problem. So after solving the problem, my array didn't look like it was before. And that is something that you need to think about in Fortran, because if you pass something to a routine, it can modify that data. Function you can also have in Fortran, but you can only return a single value or single variable. You can have subroutines in different ways in Fortran. You can place them in separate source code files, and that will mean that there is it's called an implicit interface. You have to declare everything for that routine. You need to be able to, the subroutine must have input variables that define the sizes of the arrays coming in. Those subroutines can be also implemented in C. So you can compile them and link them together, and that will work together with Fortran as well. You can have internal subroutines that are subroutine contained in the contain section of a module or a program. And you can have a module subroutine that is a subroutine contained in a module. So these are the three ways of doing subroutines. And also, if you have a main program, end program, and a subroutine after that program, that will also compile. But that subroutine is considered to be outside the program. It's like you have compiled it separately. And it's only the ones that are in the contain section that kind of goes together with the main program. So this is the syntax of a subroutine. You give it the name subroutine, the name, and then you can have something called a dummy argument list or argument list. Here you list your variables that are you want to communicate over to the subroutine. You need to declare all your variables coming in, the first thing you do, and then you have your executable code. Return will exit the subroutine. You can have multiple returns. They return back to the calling code. And then you have end subroutine here as well. And here I think you need to have end subroutine to indicate that this is a subroutine that contains a code. You don't have to have the name of the subroutine here as well, but if you have log subroutine, it can be a good idea to have end subroutine the name.
But the return is not necessary.
No, if you don't have a return, it will
to end.
Exactly. If you have if statement, that kind of a condition that I want to exit at a certain point.
Yeah.
But if you don't have a return, it will return at the end point. Yeah, all variables passed by reference. So an argument to the subroutine refers to the actual variable in the calling code. You need to declare all the variables in the subroutine, and you call the subroutine using the call statement. So in Python, you can just give the name and the parameters, but in Fortran, you need to do call, unless it's a subroutine function. And you return at the end. You return to the calling code by using end or return. So here you can see what I mean here. So I have a subroutine here with A, B, and C. A is an integer, B and C are arrays. And if you see this star syntax here, is that if you have a two-dimensional array, you actually don't have to declare this the last dimension, because you can get to the next column by knowing the number of rows in the array. So you often see this as used to don't have to give all the parameters. So in this here, A here actually defines the number of rows for B and the total number of elements in C. But these actually refer to the variables up here. So when you call it with this, the memory locations will actually be passed over here, and you will work directly on these variables here. And also you need to at least have one of the dimensions declared. So A is needed to be able to declare the size of B, otherwise it won't compile. It actually can compile, but it will not link. Because these routines, in this case here, this routine is compiled separately as a separate source code file. This main program is compiled separately, and they will be linked together. If these don't work out, you will either get a crash or because you can declare them differently here as well, which can be also lead to some interesting problems. We are not talking Rust here. We are talking, we access memory directly here.
So B and C are different from the first ones.
Sorry?
The B and C in subroutine are different from the ones in the program.
No, so if you access B inside here, you will access the memory location, this variable here. So if you assign a value to B inside my subroutine, it will assign a value to this variable outside here.
So A is 20, or we define size dimension as A, but in the program the size is 20.
Actually, I will update this because I'm not I'm perfectly satisfied with this slide.
The naming is.
Let's see where I get. Why did I jump so long? It should have been like this. or it's okay. Let's see here. This was not a good example. 10 a equals 10. This is it should look like this. So now I pass over 10 here. That will fit it, and then b will be 10 by 20. So just give it up like that. And 10 here, and a will fit there as well. So you need to kind of declare your variables with the correct sizes. You could have done, if you knew that you only will pass an array that is 10 by, you can put it, then you can skip the a here, like this. If you knew the sizes and you knew, then it will work. But if you want to have a flexible function, yeah. So then you can go in here.
The name the argument to the function, and those are, I can name them whatever. I don't need to.
They don't need to be the same.
Right. And then I declare those newly named things in the subroutine.
So you can have, for example, you can have R here, like that.
But I need to make sure that the two arrays here have the correct dimensions.
Yeah, and also if you, so that you, for example, if you lie to the subroutine, say that the arrays are 20, and you start looping in the subroutine, you will get a memory violation. So there is no protection against that. You need to make sure that you pause. I will show, this is the kind of unsafe way of doing it. There are better ways of doing this. But this is the kind of, the default behavior is that everything going in is references to the actual variables outside. It's also possible to have different data types here inside and different dimensions. So you can make it even more interesting. So if it's
checked on the linking stage,
you can it doesn't check if you compile it separate like this.
On the linking stage, when you link the files.
Depends if the number of arguments are correct. It will just link them together.
So it doesn't change. Doesn't check the dimensions. How they.
No, it's up to you. Unless if you're using modules with a count later, it will do that. But if you're compiling separately now, the main program, the functions, separate source code files, there is no checking. It's just that the number of arguments are correct. It will link them together.
And just so this is last thing, my brain followed it. So if we were to rename the subroutine B here, and just we don't need to do it, but say that we just put out a new label S, whatever. Then when I declare my S in the subroutine, I need to make sure that it has the same dimensions as the B. The main program. Or
you can say the caller must make sure that it calls the subroutine with the correct parameters. Yeah. But the thing is, there is no way of checking in this version that the sizes are correct. So functions, very similar to subroutines, except that you can assign the function name the return value. So you declare the type of the functions, or for example, real function name, and then you can do function name equals to the return value. You can also do, I think it's result equals to return value as well, but the normal thing is that you assign the function name the return value. And then it returns. So here you have So here you have real function f, then you have f equals to synex, that will assign the return value here.
Technically, the return statement is unnecessary.
Yes, let's see.
Sorry for being difficult.
Let's do this here. We take this to Compiler Explorer. I'm a bit confused now. Test. it apparently returns directly. So when you do that, it doesn't print.
They don't call the F from the main program.
Kind of meaningless function, so perhaps. Yeah, it did. So it only assigns the value and then it returns. So you can do things after assigning the value.
It assigns the value. I guess I can change that value if needed.
Exactly, and then after the call it will be assigned the final value.
But the function name is convention, or how you actually return things.
This is a.
You can do it via function name, but not necessarily.
I think you can do. So we can have.
The initial call.
You can see here that these two, the first part is compiled, second part is compiled, and then linked. Mm-hmm. That's why you get the linker error now. So there is it doesn't know about it. It compiled the program, but it couldn't link the final program. It can compile a function here. So but I think you can also do, let's see, a result. Yeah, we can do a result as well. Which? What?
Oh, well, it's sort of outside the scope of returning function name.
But okay. Oh, I think I need to declare the result variable as well. Oh. But there is a way.
Assign the function name, and when you return that function name will have a value.
Yeah.
And that's how you do it normally.
Yep.
Even though it might be other ways.
But so this is the old way of compiling. You compile the source code first separately and you link them together. You do that in a new way as well. But when we introduce modules, everything will be more clear, and also it gives you some additional advantages. So modules, you can package global data, derive data types, subprogram. You can define interface blocks, name list definitions. But the idea is that you package everything associated with some kind of task. And I think it's the same similar idea we had with Python modules. So it could be a package for interval, arithmetic, finite elements of certain types, and so on. Modules are defined almost like a program. So you have module name, specification statements, contains, and you module subprograms. So typically in the top level you declare global or private variables to the module, and then you have the module subroutines in the contain sections. Then you use the use statement here to tell Fortran, I want to use the constants module. And then it interface makes this module available in your current context. So if, for example, here you have the constants we declare for selected real kind, I put them in the constants module, and then I can use them here in my the code after the use statement. So this is a way of creating a single point in your code where you can configure the behavior of your code in certain ways. So in this case, I only have constants here. You could have variables. You can have subroutines as well. So modules here, you can also, for example, have a module truss here. You can actually have an attribute called private on your variables. And those variables are not accessible outside this when you use the module. So the user of the module can't access the private variables. You can do the same thing with the subroutines. You can have public and private subroutines. So you can do some basic hiding of things that you don't want to expose in your user interface or in your library interface. And then you can have use truss, and then it will call the subroutine inside the truss module. So you can say it's very similar to the import in Python. And also, module interfaces and functions have a lot of added benefits because it will check the parameters as well between. the modules and the calling routines. Yeah, I said before we go into the parameters as reference. We did that already. And this is the kind of discipline I want to show you here. So I have a program here, old style. You have to define for each parameter, array parameter, you need to define rows and columns and number of elements. And you have to declare the variables here with the variables so that it matches the incoming here. And notice here I have actually done a trick here. So in this subroutine, I interpret A as rows times columns. And that is perfectly fine. You have to make sure that you have enough elements here so you don't access outside, but that you can reinterpret if you want to. Then you can do all that stuff here that we put. If everything is defined, you can use assign A all values 42 here. Yeah, and we have that already. So if you're using modules, you can declare, instead of using the star and the explicit number of dimensions, you can use colon, colon, or colon as the dimensions. And the declaration is in a module subroutine. And also, you don't have to pass along the sizes of the arrays. You can actually just pass over the array names. And then you can query the sizes of the arrays coming in using the size statement. So here, in this case here, I have this is the old style, rows column here. Then we do a module here instead. We put the subroutine in a module. And now, all of a sudden, we get access to a completely new syntax. So you can see here, I can declare my A here with colon, colon. I can do A equals to 42 here without having the exact size of the array. I can query the size of the array using size A,1, which is the number of columns, A,2, number of rows and the number of columns. And I can call it just with my sub A. And this is not possible if you separately compile. There are some tricks, but they're really complicated. Using modules enables this automatically. Same thing if you put the subroutine in the contain section of a program, you get the same benefits. So the contain section of a program can be considered a small main module in your code. Yeah, if you put it here, you get the same benefits. But if you have moved this outside after the end program, it wouldn't work. So modules brings a much simplified calling interface to Fortran. It will reduce the number of parameters significantly by not having to specify the sizes of the arrays coming in. Yeah, and then, as I said, there is a way of doing it anyway. And then you have to tell Fortran what interface this subroutine has. So you can do interface subroutine, and then you declare the interface here, and then you can do the same thing without having a module. But you can agree with this is more complicated than having modules. And modules are just, you have module and module contains, that's it. So those, it's very easy to do. I think we'll stop here, and I will take the next part, I think next week here, and I will do some short examples of how to use IDE for Fortran as well.